So today we have with us yet another awesome PhD student in the Institute, Tom Manzini, who's a PhD student at Texas A&M. And his work really focuses on computer vision in machine learning, specifically increasing the robustness of applicability of machine learning to support operational decision making. So great topic of relevance to our institute. And Tom has a bachelor's from Rensselaer Polytechnic Institute, and also, as so many others, his path has gone through Carnegie Mellon, where he was a student, I believe, in LTI. Is that right, Tom?
Yeah, that's correct. Yeah, I have I was in the Masters of Language Technology degree program.
So master's from CMU, is working on our disaster thrust with Dr. Robin Murphy. And before he came back to academia, he was in industry, worked at Microsoft as a machine learning scientist. And interestingly, is also a commercial pilot, has a commercial pilot's license, and also has a lot of experience as a emergency medical technician and firefighter. So his heart's in the work for sure. And there's a lot of exciting work in the disaster thrust coming out of Texas A&M right now. So at this point, I'll turn it over to Tom.
All right, thank you. Yeah, and I'm excited to talk about this. Kind of as Norm alluded to, this kind of hits on the intersection of three of the sort of areas of experience that I've got. You know, I've got that background in machine learning and computer science from CMU and RPI and Texas A&M. Background in aviation, both in manned and unmanned aviation, and also in emergency response. So we're going to be talking today about the intersection of all three of those, sort of unmanned aviation, computer vision, and emergency response. So that leads us to today's talk, which is a presentation of a data set that we've been developing. This is work that I've really just been lucky enough to be a part of. As you can see here on the title slide, this is work that I've done along with colleagues Priya Parali, Raisa Karnik, and Dr. Murphy. Dr. Robin Murphy is the PI for this work. So this is a talk for AI-SDM. So there's a societal decision-making problem that's really at the core here. So that is so when a disaster happens, drones, manned aircraft, and satellite all go to the scene of the disaster, and they all collect imagery in order to show local conditions at the scene. Now, recently, drones have really become a go-to tool for a couple of reasons. They're cheap, they're easy to deploy, they're immediately available. It's not like you need to wait for the airplane to come from out of state or for the satellite orbits to line up. And also for extreme weather events, they can fly below the clouds. And so there's really a nice opportunity here for drones. And so with that, sort of there's a need for supporting the decision makers who are going to be leveraging that data in practice. So now with that in mind, let's talk about how drones are used, have been used. So this is data from Hurricane Ian. And Hurricane Ian hit on the 28th to the 29th, kind of in the nighttime there. And then there were about 3 to 4 days, which we would call the response phase. And this is where sort of immediate life-saving activities are taking place. And you can see here that the vast majority of the stuff that drones are being asked to do during this time period is sort of assessing needs and doing reconnaissance, just kind of getting the drone up in the air and figuring out what's going on. There are two types of data. There are two data types that can come out of this type of work, and we're going to talk about one of those in a moment. Now, the societal decision-making question comes in quickly as the data is collected. So teams go out and they collect data, and ultimately that data needs to make its way to a decision maker. And here you can see on the right-hand side, you can see a plot which shows the distribution of data that was collected over time. So here on the 29th, I'll use my mouse to indicate, on the 29th, there were a couple of hours here where it collected 15 gigabytes of data and maybe 25 gigabytes of data. And you can see this is sort of gigabytes per hour. Each one of these each one of these vertical bins represent gigabytes per hour. Now, the horizontal bars here represent the upload speeds that were observed in the field. And anytime one of these blue bars surpasses the horizontal line, that means that there was more data collected than could have been uploaded at that speed. And so what we see here really, like, especially on the first into the second, the drones are just collecting way more data than could reasonably be uploaded from the field. And so what this means is that the drone teams go out, they start collecting their data, they continue collecting their data. And by the end of this day, there's been this sort of backlog of data that needs to make its way to a decision maker. And it's built up. The wireless networks can't handle it. And so now it needs to be physically transported to decision makers. And so imagine that you're a decision maker who tasked a bunch of drone teams to go out and collect data for you, but they've arrived at the end of the day and they've just dumped 400 gigabytes of data on your desk, and now you have to make sense of it. That's a difficult problem that would be called a data deluge in practice. And these happen pretty consistently every disaster. It's not I don't think I've heard of one where the communications and the wireless infrastructure was not a pain point. So this is a problem that's been reoccurring for a while now. So really, we kind of want to jump ahead and say, what sort of questions are these decision makers using this drone imagery to answer? And this is reconnaissance imagery. And so there's really one big question, which is sort of where's the damage? Where's the bad stuff? And really, we have a couple of things that we can use to align on that, let's sort of detect the bad stuff. But the big one pretty consistently is buildings. And so that leads us into the data set that we'll be presenting today, which is the CRASAR-U-DROIDs data set. And this is a data set of orthomosaics. So we're going to talk a little bit about what orthomosaics are in a moment, but it's basically a collection of images, and I'll show you some examples in a moment. But this is a data set of imagery collected at 10 different federally declared disasters in the United States. There are 52 of these orthomosaics, and inside of these orthomosaics, there are 21,716 building polygons, each of which has been annotated for a damage category and also has been aligned spatially to bring those polygons into alignment with the imagery. We'll talk about that again in a little bit. In total, it's 68 kilometers squared of area and 67 gigapixels. And we've also got, again, we'll talk about alignment and adjustment later, but 7,880 annotations for that spatial alignment. Now you can see on the right-hand side a table which shows the distribution of data. You can see that Hurricane Ian represents a large proportion of this data set, but we also have tornadoes from the Mayfield tornado, a volcano eruption, and the Kilauea eruption, a couple more hurricanes, a fire, and then a man-made collapse. Now, I've mentioned this a couple of times, but an orthomosaic, sort of what is an orthomosaic? So this is one of those data products that drones collect in the field at a disaster. And it represents a collection of raw images that have been fused together and sort of overlaid, mosaicked, if you will, into a larger image. You can think of this as sort of a very high resolution of Google Earth or something like that, in that it's a view of the world from above. And it's also got this nice property, which is that each pixel has a latitude and a longitude assigned to it. So that means we can plot things like spatial data, things like building polygons or road lines on top of this imagery and see where they line up. Some examples of these orthomosaics are shown here on the right. So you guys can hopefully get a sense of what these images look like. So we've talked about orthomosaics. Let's talk a little bit about building polygons. So building polygons are kind of exactly what they sound like. It's a polygon that represents the building that exists at that point on the Earth. And you can see on the left here, sort of zoom in of one of those larger orthomosaics. The building polygons here have been overlaid on top of these buildings in the imagery, and they've been annotated for their damage category, and you can see the color represents that category. So red represents buildings that have been destroyed, orange represents buildings that have sustained major damage, yellow represents buildings that have sustained minor damage, and green represents buildings that have sustained no damage or no visible damage. You'll also notice in the top left, these buildings have been aligned with the imagery. These building polygons have been aligned with the imagery. We'll talk a little bit more about alignment, but just keep that in mind that there's a little bit more complexity here. So we've talked a little bit about the societal decision-making problem, but there also are some opportunities that we wanted there's also some gaps in the literature that we wanted to address in building CRASAR-U-DROIDs. The first really hits on that societal decision-making problem that we referenced earlier, which is, we want to build computer vision techniques that are able to actually move the needle operationally for disaster response. But also we wanted to collect and annotate data that would be useful for the computer vision and machine learning community. And that specifically comes in the form of multi-scale imagery. And we'll be talking about that a little bit more in detail in a moment. But before we jump into that, I do want to cover some related work. So let's contextualize the CRASAR-U-DROIDs data set with the rest of the field. So in terms of pixels and in terms of square area, it's the largest data set of disaster imagery collected from drones that's, at least we're aware of, that's ever been published. More than an order of magnitude more area covered, and it's also more pixels than any other work previously. It's also the only data set that focuses on orthomosaics, and it's also the only data set that's got that property of georectification, which means that each latitude and longitude has each pixel has a latitude and longitude. Comparing again to manned aircraft and satellite data sets, we have the LADI data set and the Volan data set in the manned category. Those are both oblique data sets, so they contain imagery that is not georectified, and it's looking at buildings from sort of an angle as opposed to that top-down view. In the satellite world, we also have XBD, which is a data set of damage assessment a damage assessment data set from satellite imagery, along with the ABCD data set, which focuses on tsunami damage in Japan, the IDA-BD data set, which is Hurricane Ida, and also Haiti BRD, which is the Haitian earthquake. Now, comparing our work to other SUAS data sets, we can see that there is a little bit of a distinction in the source of the imagery. So the CRASAR-U-DROIDs data set, RescueNet, and FloodNet are the only data sets that are sort of sourced from data that was collected operationally. So this doesn't mean that they were not scraped from YouTube or pulled from data that was posted online. These were images. The data that's contained in these data sets are representative of the sort of data that would be collected operationally, but also representative of the types of damage that we can see in actual disasters, as opposed to those that may not be maybe slightly edited and posted online. And this also provides a little bit of credibility, and it's heartening when we talk to emergency managers to be able to back it up and say, this data set, we can really trust it because we've gone through the effort to make sure that all the data that's in it is operationally valid. Now, in terms of the type of damage that's present in this data set, it also is the most expansive in the literature. So this data set, the CRASAR-U-DROIDs data set, covers hurricane damage, both in terms of storm surge, wind, and flood damage. It has tornadoes, tornado damage, a volcano eruption, fire, and we also have man-made collapse. In the past, data sets have focused almost exclusively on hurricane damage, with the exception of ISBITA, which contained hurricane damage and one tornado, and tornado damage from some unknown tornadoes that were not included in the publication, were not referenced in the publication. So what do these other data sets look like? So on the left here, we have RescueNet. On the right, we have FloodNet. Focusing in on the building damage component, because that's really where CRASAR-U-DROIDs is interested. These two data sets addressed building damage from a schema that they created, labeling it as building no damage, medium, major, or total destruction on RescueNet, or building flooded / building not flooded. These image data sets are not geo-rectified, and they also represent a smaller spatial area compared to CRASAR-U-DROIDs, being 3.6 kilometers and 2.85 kilometers respectively. Moving to manned, the biggest one or the most important one to reference is the LADI-V2 data set. That's the low altitude disaster imagery data set. It's oblique imagery that was collected by the Civil Air Patrol across a number of different federally declared disasters in the United States. So these are people who are in aircraft flying over the scene and then holding cameras out the window to take photos of the damage. They labeled for a number of different categories, but most relevantly for buildings. Those were buildings any, so are there any buildings in the image? Were the buildings affected, minor, major, and destroyed? And so those categories align with a FEMA damage assessment scale. And so this is an instance where the labels generated for the data set align with the operational use case. And then jumping to the satellite world, XPD. So this is a data set of satellite imagery over areas of disaster. They introduced the joint damage scale, another scale of their creation, but was created in concert with a number of different government agencies to ensure operational validity. So this is no damage, minor damage, major damage, destroyed, and unclassified. And then the other one to mention is ABCD. This was one of the early works on building damage assessment and satellite imagery, focusing on damage assessment for the Japanese tsunami. And the schema here was simply a binary: was the building washed away, or was it still surviving? So the imagery in this data set and others like it that we referenced earlier, they're all geo-rectified and they all operate on orthomosaics, but they operate at a much lower resolution compared to drone data. So this is imagery that's in the sort of 30 centimeters per pixel range, whereas the drone imagery that we're working with is closer, is in that 3 to 8 centimeters per pixel range. So much higher resolution, almost an order of magnitude in some cases. So I guess with that explanation of the literature, let's talk a little bit about what is actually in this data set. So raw imagery was taken at a number of different disasters, 10 different disasters in this case, from the course of 2017 up to 2013 with Hurricane Idalia. And this includes specifically Hurricanes Harvey, the Kilauea volcano eruption, Hurricane Michael, the Musket Bayou fire, Hurricane Laura, the Champlain Towers collapse, Hurricane Ida, the Mayfield tornado, Hurricane Ian, and then Hurricane Idalia. And the way that this imagery was collected was that at these disasters, a number of different drones were flown at each disaster, but in concert in the data set, 8 different models of UAS were observed, or data was collected from 8 different models of UAS. So that's the DJI Mavic, the Matrice line, Phantom, the Paradenofi, the SenseFly EB, and the Wingtra. Those drones went out, they flew at those 10 different disasters, and in total, they collected around 48,000 images, which represented just under 700 gigapixels worth of imagery. Now, this is the point at which the previous literature on drone disaster damage assessment stops. You take these images, you plug them into a machine learning system, and then out pops an answer for that image. But that's somewhat different from how these drones are being used practically. Practically, these images are further processed by being fed into these 2 different orthomosaic mappers. In this case, we used Pix4D and Agisoft Metashape. And then we processed those, and they were also processed in the field. Like in the operational setting, they would have been processed for the construction of this data set. They were processed into 52 orthos, and those total 67-ish gigabytes, or excuse me, gigapixels worth of imagery. And the CRASAR-U-DROIDs data set focuses on these orthomosaics, these combined tiled images, as opposed to these raw images, which would have been further processed in practice. Now, how did we go about annotating this data? This was one of the big process. This was the really big effort associated with this work, and so let's talk about it. We took those orthomosaics, and we tiled them up either into tiles of 2048 by 2048 or 8500 by 8500. We'll talk about the reasons why in a moment. And then we took building footprints generated by Microsoft, and we overlaid those building polygons, or those building footprints, on top of those images using those latitudes and longitudes that are associated with those pixels in the images. We then performed annotation. So in the case of those really large, those 8,500 by 8,500 tiles, we did what's called bulk annotation. So these were exclusively orthomosaics where we knew there was very little or no damage at all. And so we reserved those images for ourselves, sort of as the authors, to look at individually and explicitly mark where damage was, as opposed to mark independently or mark entirely each building anew. In the case of those 2048 by 2048 tiles, those were what we presented to our pool of annotators. So here, we would ask an annotator to look at the tile and look at the buildings in those tiles, and we would ask them to assign a label. And so then it entered this review process where we would look to see, are these buildings annotated at all? If they're not all annotated, then we would reject them and send them to another annotator. If they were, we would inspect them for correctness. If there were issues, we would reject them or correct them ourselves. And if they all looked good, then we would approve them and they would get sent off to the next step. So in total, we rejected or corrected in some way just over 10% of these tiles. In total, yeah, just under 2,000 tiles were corrected or rejected. So then at this step, we combined the annotations from the bulk annotation process and the annotation and the hand annotated process, the approved tiles, and we combined them into a orthomosaic and presented the building polygons no longer laid atop individual tiles, but laid atop the entire orthomosaic. And this prompted another round of review to make sure that the process by which these building polygons were combined into an orthomosaic were correct, but also to make sure that the annotations themselves, the review process that existed beforehand, didn't allow any additional noise to creep in. So again, we looked at these entire orthomosaics with these building polygons laid atop of them and asked ourselves, are these annotations correct or not? In some cases, we found that they were not. And this was a review by committee. So this was several people sitting together looking at an orthomosaic and judging whether or not these building polygons were correct. In this case, now we're talking about building polygons, no longer tiles. We opted to correct just under 6% of those building polygons. Yeah, in total was just under 1,300 building polygons changed during the second stage of review. And then here, we also took the opportunity during this orthomosaic level review to check whether or not we wanted to add any building polygons. So if there were any building polygons that were missing and the committee agreed to add those additional building polygons, then we went in and did so. And we only did this for 108 buildings, representing less than 0.5% or just about 0.5% of the buildings in the final data set. And then with all of this done, these building polygons represented the gold portion of the building polygon data set, and this became finalized, so giving us a total of 21,716 building polygons. So this is really the flow that we took from getting data to annotating, reviewing, and then finalizing those building polygons. And the reason why we took this two-stage process was really in an effort to mitigate noise. We wanted this data set to be a benchmark for machine learning models for this, for this use case for building damage assessment from drone imagery during disasters. And so we wanted to make sure that the amount of noise in this data set was kept to a minimum. So we've talked now about annotation, but what was the scale that we used? Like, what were the things that were actually presented to annotators? So in this case, we used the joint damage scale. This was the data, excuse me.
Tom, we lost your slides.
Oh, hold on. Let me know if it comes back.
Yep, it's back. Thank you.
Wonderful. So yes, in this case, we used the joint damage scale, which was the damage schema that was presented in the XBD paper. There are four damage labels associated, or that could be associated with each building, and then a final label for buildings that could not be classified. So no damage represents buildings that are undisturbed, no signs of flooding, just a normal building. Minor damage represents buildings that may be slightly burnt, or in the case of flooding, water is touching the structure. In the case of lava flows, lahars, again, touching the structure, or you may have a roof that's slightly cracked or discolored, tiles may be missing, stuff like that. Major damage represents buildings that have sustained structural damage. The structure has been affected, so it's no longer superficial. So this could be a wall collapse, roof partial collapse, or partially missing of the road. In the case of flooding, water surrounds the structure. In the case of lava flows, yeah, lava surrounds the structure, but the structure is still present. And in the case of destroyed buildings, the building's gone, it's scorched, it's submerged by water, or it's completely, completely burnt to the ground, or it's covered by lava, covered by water, covered by mud. Building's no longer present. And then the last case is this case of unclassified buildings. So these are building polygons that are, excuse me, it's reserved for buildings that are no longer present in the imagery, but do not have any obvious structure or foundation or debris pile that's associated with that building polygon anymore. So the assumption is that these building polygon, or the buildings associated with these polygons, were removed, like a human came in and raised the lot before the disaster happened. So we want to be able to distinguish between these types of absent buildings and buildings that have been destroyed. So why did we go with this damage scale? The reason is really because of it's well aligned with the use case. Obviously, like we're assessing building damage. This is a building damage scale. But it was also developed with input from federal organizations, so NASA and FEMA, and also leveraged the literature fairly heavily to ensure that the damage classes were aligned. And also, the emergency managers, they may be familiar with this scale as well. And so it's an opportunity to not have to make disaster managers learn an entirely new scale, an entirely new output schema, just because we've introduced a new tool into their workflow. And then lastly, there's an academic advantage to this. Because we have the XBD data set, which has been annotated using the same scale, it gives us an opportunity to compare and contrast the transfer of machine learning techniques that have been trained on drone data and are now being tested on satellite data, or vice versa, to see what the deltas are as we change image resolutions. So now with that damage scale in mind, we can talk a little bit about the distribution of damage that we see in the data set. So we see the vast majority of data of building polygons in this data set are not damaged. So that indicates a scenario where a drone went to an area and it didn't find any damage. But then there are sort of in descending order of damage intensity: minor, major, and destroyed, where destroyed represents just under 1,400 instances of destroyed buildings. And then unclassified represents the lowest category. So there are very few instances of buildings that have been destroyed by a process that we do not, or are no longer present, and we think it's because of a process that was unrelated to the disaster. In total, it's 21,716 buildings. And another question is, these buildings don't exist in a vacuum. There's this question of where do these buildings themselves come from? So we can see here the distribution of disaster events, the distribution of building polygons grouped by their respective disaster event. So in the case of the man-made collapse of the Champlain Towers, we only have 4 building polygons associated with it because it was just such a tight, small area disaster. And then moving up from there, we have the Musset Bayou fire, the Kilauea eruption, and then you can see this sort of these groups of blue, which represent hurricanes. And so you can see that we've got Hurricane Laura, Idalia, Ida, Michael, Harvey. The Mayfield tornado representing the second largest proportion of data in this data set, and then finally Hurricane Ian. I will mention this data is in log scale, so just be conscious of that. But one thing that you can see is that, this data is in log scale, and also each color here represents a different type of disaster. So the purple of the Champlain Towers represents a different disaster than the blue of the hurricanes. And you can see here that there is a heavy tilt in this data set towards hurricane-related building damage. And that's one of the things that we have to be cognizant of as we think about deploying models that are trained on this damage, on these building damage samples. So early on, I kind of glossed over this, but I called to it something that we would talk about. These building polygons that we get from Microsoft and the imagery that we collect in the field, those two sources of data are not always aligned with each other. And this can be caused by a number of different reasons. So there could be GPS noise in the drone that went out and captured the imagery, or in the satellite whose imagery was used to derive the building polygons. These building polygons are derived from satellite imagery. It could be caused by errors during the conversion from the segmentation masks, which were generated from the satellite imagery, the conversion from those masks to polygons. It could also just be it could be a result of a sort of natural imprecision. These satellite images, which are used to derive these building polygons, are taken at a lower resolution compared to the drone imagery that we're working with here. So there's just a natural chance for imprecision as we move from lower resolution data that was used to derive the building polygons to high resolution data that we're working with now. And then also there could just be errors that are introduced as a result of georectification, which is that orthomosaic, that tiling process that gives us the entire orthomosaic from those individual images. So as those images get interleaved or mosaic together, they get shifted around a little bit and warped and skewed to make everything line up. There's an opportunity for noise to be introduced there. And you can kind of see this in the top line above, excuse me, in the top image above. You can see the building polygons with their damage classes colored in. They don't quite overlap with the buildings themselves. You can see they're all kind of shifted down a little bit. And it's highlighted here with these red circles for additional context. Now, if we're going to be training machine learning models on this data, or if we're going to be performing inference on this data, we need to deal with this alignment problem. We're calling it an alignment problem as opposed to registration or something like that, which other people may be familiar with. But we're also thinking about, as we want to work towards multi-platform models, machine learning models which consume more than just drone imagery, maybe they consume satellite, drone, and other sources of data as well. We need to make sure that this imagery, or the units at least that we care about pulling out of this imagery, in this case building polygons, align well or can be aligned well with the imagery. So we want to make the top image, that misaligned version, look like the bottom version. And this is kind of a little bit of a preview of what I'll show later, but this is something that we know will induce bias in machine learning models, certainly during inference, but also during training. So you can see here on the left, we have images that are 5 buildings, all of which are undamaged. We pass in building polygons, which are misaligned, and then we ask the model to perform inference, label each one of those pixels as if it's doing a segmentation task. And when we look underneath, we kind of lift up those building polygons and we see what's underneath. We can see that the buildings have been labeled as mostly green, which represents that no damage category. But we also see that there's a good chunk of the buildings or the area under those building polygons which have been labeled as purple, which corresponds to that unclassified label. So in this case, the model had learned that, clear grass with nothing going on, we should probably label those pixels as unclassified. And as a result, the model has sort of let that bias creep into the areas underneath these building polygons, which are then going to be used to provide labels for those building polygons. So it's not just a training problem, it's also an inference problem. And I'll give you guys a little bit of a spoiler. This is something that we saw pretty extensively during our response to Hurricane Debbie, or our participation in the AI response to Hurricane Debbie, I'll say. More on that later in this talk. So we wanted to correct for it, and we're still in the phase where we're building a data set. So we wanted to make sure that we could, one, have a data set that dealt with this problem so that it wasn't a problem for people who just wanted to train models and not worry about alignment. But also we wanted to generate labels in order to hopefully downstream train machine learning models to perform this alignment automatically. So in order to do this, we, again, tiled up the orthomosaics into tiles of 8,500 by 8,500. We then overlaid those same building polygons like we did earlier. And we then went in and manually provided adjustments. And so adjustments are sort of, you can see one of them over here on the right here. That represents, this arrow represents an adjustment. And it's a movement that takes a building polygon vertex and brings it to the location of the building where we think it belongs in reality. So you can kind of see it as a linear shift for each one of these building polygons. So we then use these individual adjustments to form a vector field. which is then used to adjust all the building polygons nearby it. And so we kind of go through this iterative process where we take the adjustments, we generate a vector field, we look at the resulting building polygon alignments and say, do we think this vector field is sufficient to correct for the alignment issue that we're seeing? If it isn't, then we go in and we add more adjustments to sort of pin down that vector field. If it is, then we get to finalize it and say that we're done here. So in total, we generated 7,880 adjustments. So that represents an adjustment for a little bit over every third building. 1 in 3 buildings got an adjustment. And the remaining buildings which were not explicitly adjusted were brought into alignment by that vector field that I referenced earlier. And so that's how we jump from the 36% of building polygons adjusted to 100% of building polygons aligned. And so we're hopeful that this will be useful for training machine learning models so that they either can perform damage assessment without building polygons, like we just want to generate a mask, where's the damage, go for that, but also to bring building polygons into alignment so that we can interrogate those specific building polygons and see what the model thinks about the pixels that are under those polygons. Just a little bit more detail here. I know this concept of a vector field might be a little dense off the bat. So this is sort of just a visualization of one of those vector fields on top of one of those orthomosaics. So here we have an orthomosaic. You can kind of see it as a little bit transparent. And overlaid on top of it is that vector field that's used to adjust the building polygons in this image. So you can see on the left-hand side, those building like up here in this corner, for example, these building polygons get nudged up and to the left, whereas over somewhere else, they get nudged down into the left here in the center. So it's a field that sort of translates these building polygons around. So we've covered adjustments, we've covered the data, we've covered the process by which we annotate the data, we've covered the process by which we have collected the data. The next question is, we're building a benchmark data set, so we want to provide train and test splits for people who use this data set to work with, so that they know how the performance of their models stack up with with other people who are using the same data set. Now, the question about how to come up with that train and test split is not a clear one. So if you're just thinking purely from a theoretic perspective, you would have data that's truly IID, and your test data set would be sampled from the same distribution as your training set, and so you'd just be able to do random sampling, and you pull out some samples to then be used for testing. However, in the disaster scenario, there's not you don't have the guarantees of the data being IID. And there are also a number of operational considerations at play that may want you to, or that may drive you to choose a different type of split. So now, with that in mind, ideally we want the test scenario to be as close to the actual use case, the end, sort of the operational use case for any trained machine learning models. And because we're working in the real world, there's some considerations as how we mirror that operational use case in this train and test split. So the first one is a geographic split. So you could imagine the model is a disaster has occurred, and it's in a geography that the model has not seen before. So that could be like, when I say geography, that could be like the next city over, like it's just it's in the same sort of state or in the same type of terrain, but it's just buildings that the model's never seen before. So this is kind of akin to like training on the north or testing on the south, or like training on areas that you've never seen before. So that's kind of option one. It's just, and the motivation for this is that it's rare but not uncommon for disasters to strike the same location twice. So you want to make sure you're measuring the performance of your model in these new geographies. The second next option is that there may be temporal changes at play, or temporal dynamics at play, that you want to account for. So for example, as building codes get changed, as new buildings get built, there's sort of a cat and mouse game between building engineers, civil engineers, and disasters. Disasters represent instances where the mitigations weren't sufficient, and so it represents a out of distribution case. And so as civil engineers and building code the people who approve building codes are making changes to try and prevent disasters. There's a kind of cat and mouse dynamic, and so you might want to consider training on the past and testing on the future. Again, sort of jumping back to geographic and temporal, both of these we decided weren't really practical for us because of two reasons. For the geographic scenario, we've got this heavy bias from Florida and from the American Gulf Coast, and so if we were to do a geographic split, it would represent we'd just end up with an unbalanced data set. In the temporal split, it would be similar because there's a similar dynamic at play, which is, drone use is increasing over time, and so we're getting more and more data from drones. And so we generate, if we were to perform a temporal split, we would get an unbalanced data set. The last option, which we didn't go with, was a disaster type split. So this is, you can imagine, a new disaster has occurred, a type of disaster that your model hasn't been exposed to. And so you want to measure the performance of your machine learning systems on those held out disaster types. So this would be something like training on a hurricane and testing on a wildfire. And again, we decided not to do this approach because we do have that heavy bias towards hurricanes in our data set. And so the choice that we ultimately went with was a disaster split, a disaster type split, or excuse me, a disaster split, where we train on some held out set of individual disasters, and then we test on other held out disasters. We argue this is kind of a good compromise. There are these other dynamics of new geographies and changes in the sort of distribution as time goes on. But it aligns well with the operational use case of a new disaster has occurred, potentially in some new geography, potentially in some at some new point in time, and a new disaster has occurred. We got to go and run the model, and so this is what we settled on. But now the rubber has to meet the road. So it's nice to have these kind of academic discussions, but we had to make a decision for our data set. And so ultimately we chose to do, as I mentioned, that individual disaster split. So we moved all the data from certain disasters into the training set, and certain data from all the data from other certain disasters into the test set. So in the train set, we have hurricanes Ian, Ida, Harvey, and Laura. We have the Kilauea volcano eruption. We have the Champlain Towers collapse. And then in the testing set, we have the Mayfield tornado and the Musset Bayou fire, both of which are disaster types that were not seen in the test set. So we tried to include some of those dynamics. And at the same time, the Mayfield tornado occurred in Kentucky, which is a locale that's outside of Florida or Hawaii, where the training set was selected from. And then we also have hurricanes Idalia and Michael in the test set. Roughly, there are a couple of different ways to describe this split, but it's somewhere between an 80-20 and a 70-30 split, depending on orthomosaics, depending on how you measure in terms of orthomosaics, kilometers, pixels, or individual buildings. So that covers the data set. That's the data set that we have released and is out there. So I think I've still got a few minutes left. So let's talk about some of the ongoing and future work that's associated with this effort. So we've been talking heavily about building damage assessment. We have trained two models. First is a UNet model, an attention UNet model, and the second one is a VIT large based on Scale MAE's pre-trained architecture. Both of these models are performing better than random, which is what you'd hope to see. But we are seeing better performance out of the attention UNet right now. In terms of the inputs to these models, both of them receive a red, green, blue, channel image plus an additional channel corresponding to the building mask, sort of the locations of those buildings. In the case of the UNet, it's 2048 by 2048. In the case of the VIT, it's 1024 by 1024. And we're asking these models to predict a 6-channel output, one for background, and then the remaining 5 channels corresponding to the damage classes in the joint damage scale. You can see on the right, these. You can see down here, this is the confusion matrix for the attention UNet. There is some confusion between the no damage and minor damage cases, but the model seems to be performing pretty well at picking out major damage and destroyed. One of the nice things about this is that these models, or at least the attention UNet, has been constructed as a baseline, but also as sort of as a starting point for developing models that can be reasonably deployed in practice. And so when we were performing inference for a single orthomosaic, this inference occurs in well under 5 minutes on the type of hardware that we'd be able to bring into a new disaster with us. So speaking on new disasters, let's talk for a moment about some of the inference that we did for Hurricane, excuse me, not Helene, that should say Hurricane Debbie in Pennsylvania. So following the deployment of some manned aircraft going over areas of Tioga County in Pennsylvania, we ran our UNet model on imagery collected from those manned aircraft. And we haven't had the time to perform a structured evaluation of these labels, but they appear reasonable. And in terms of the timeliness, we were able to work through about 400 gigabytes of imagery in under 12 hours. And the biggest limiting factor for those numbers, or excuse me, for those 12 hours, is not the model running. It's actually just downloading the data. So the data was on the cloud, but we needed to download it to a machine where we could run the models. And so that was the bulk of the time. Sort of ballpark estimate, I would say that at most, we spent probably an hour of GPU time in total to do inference here. One of the other things to mention, this inference that we performed was unaligned. And that did result in some misclassifications, and I'll show an instance of that later on in a moment. So the model was able to detect building damage. So we were able to identify destroyed buildings like this one, and we were also able to detect buildings that had no damage like this one. But you can see sort of there's an issue of misalignment here. The buildings that are the building polygon isn't quite lined up with the building footprint, and that resulted in misclassifications in some instances. So here we have two images that were taken by the manned aircraft of the same area, and you can see in one image the building polygons. The camera didn't have a really good lock on where the image was taken, and so the building polygons got shifted off up and to the right a little bit. Whereas in the image on the right, building polygons were better aligned, and so we got better labels. And so this is an instance where alignment represented misclassifications in practice. And so it's something so this alignment problem is something that we're going to be spending some time on. I think we can say it's a problem we are spending time on right now. Now, moving off of inference that has been performed in practice, we are also looking at sort of how do we reason across multiple sources and multiple scales of data. So as I mentioned, sort of right at the beginning of the talk, drones aren't the only providers of imagery during disasters. You also have manned aircraft like we saw in Pennsylvania, and we also have satellite imagery, which is collecting photos of the scene. But there is a sort of a tough scale problem here. Like the same space on the surface of the Earth is being represented across a number of different pixel scales. And so as we think about training machine learning models in the future to reason, to deal with this type of imagery, we don't quite know what scale of imagery we're going to get a priori. And so we need to be able to have models that can adapt to these sort of wide ranges of scales. On the left-hand side, about 3 centimeters per pixel. On the right-hand side, closer to 30 centimeters per pixel. And I think you can see the difference there. One of the other things we're looking at, excuse me, is road condition assessment. So we're thinking a little bit about like what label schemas are appropriate for road damage. How should alignment be performed for roads? In the case of buildings, you've got these nice atomic, like individual structures that can just be shifted around. Sort of roads are a continuous line, and so there's we need to think a little bit differently about how roads are being brought into alignment. And we're also thinking about debris, sort of estimating locations of beach sand. That's a big problem. Sort of bringing beach sand off of places and either cleaning it and putting it back on the beach or discarding of it. And sort of what are the units for that type of prediction? Are we interested in residential plots, or are we interested in generating a segmentation mask of where is the debris in this image? And so that's the sort of thing that we're looking to decision makers to sort of help us with. So that brings us to the end of the talk. I'm happy to answer any questions, but just to start, to summarize, we'd love to collaborate. If anybody here on this call and this talk has found any of this interesting, please reach out to us. We think we've got a pretty good starting point for training machine learning models on this type of imagery. It represents the largest data set of operationally valid and known source SUAS disaster imagery. It's the first data set that's explicitly accounted for this geospatial alignment issue that we're talking about. We haven't gone out and annotated it, but we're working. But we have in our possession parallel multi-platform data, so SUAS, manned, and satellite data for these locations where we already have annotated drone imagery that we're working on experimenting with. We've got the annotators that we're going to be that we used to help annotate our data previously. We're going to be, hopefully we're continuing to engage with them. And we also, have transitioned some of these models to practice. So in the case of the Pennsylvania Emergency Management Agency, that's PEMA, we worked with them, and we've also had the chance to run these models in Florida for drone data collected during the response to Hurricanes Helene and Hurricane Debby. So the data set is there, and I think we've still got a few minutes for questions. So yeah, thank you.
Hi, Tom. Very nice work. I'll go ahead and ask the first question. Actually, I have maybe two. The first one is just a clarification. So what you did for like Helene here and so on, is that was that building damage assessment or just the identification of the like the buildings itself?
Yeah, so let me go back to that slide. This is, I would call this building damage assessment. So here you can see, so we've colored I should have clarified this, yes. The building polygons are colored based on their damage label. So this building polygon, which was provided to the model ahead of time. So we knew there was a building here. The model looked at that polygon and said the pixels under this building polygon correspond to a destroyed class.
Okay.
So that's the type of assessment.
Right. And so then maybe the follow-up question is like, have you thought about, I mean, of course, you can try to correct it via alignment completely, but like, is there both for alignment, but also generally interest in giving uncertainty bounds around that, whether it's uncertainty in the label or uncertainty in like, location?
Yeah. So I think I can just answer that question with a yes. Sort of when we were working with PEMA, they asked explicitly about confidence bounds on these predictions. And so that was something that we at the time were able to provide. I think we're still working through the calibration of those confidence intervals or those confidence bounds for each label. But I think from the sort of end user or from the decision maker perspective, I think that's something they are explicitly interested in.
Okay, and so like what type of bounds, if I may, are you looking at there? Like, is it like based on softmax probabilities and calibrating them like post hoc, or is it something like conformal predictions? Just curious about like what you're doing.
So right now it's closer to those softmax probabilities that we try and calibrate during model training.
I see. Okay, we should talk about that.
I think there's room for both.
Yeah. There's a bunch of work going on in the institute where people are trying to look at this like more. So there are other uncertainty quantification methods that may be helpful and are more easy to apply directly.
If there's anybody on the call or if you know anybody who's interested, I'd love to have a conversation about that.
Yeah, I'll ping you separately on Slack.
Sure. I see one question in the chat. Do you utilize in-house annotators, crowdsource citizen science, or outsource prior to committee review? So that's a great question. I guess it's closer to the citizen science, but it's technically neither of those. So we actually went to high schools in and around sort of our location here at Texas A&M, and also to the Winchester Thurston School in Pittsburgh, and we engaged with their high school students to provide these annotations. So the students looked at this imagery and provided those annotations, and then, as you said, we went through and reviewed during that in that two-stage process after the fact to ensure correctness.
Hey, Tom, can you go back to the slide where you show the vector map of like the misalignments? Yeah, that's one. Exactly. Yeah, this is really interesting to me because I am familiar with this concept of misalignment, but in a completely different context. And I'm wondering, and you may have said this, but then I have a follow-up question. Is there typically like a pattern? Because it looks like in certain areas it looks like there's little localized areas of patterns in this. And what is the mechanism that causes that, if so? Or is it truly like specific to each field?
Yeah, so there's a lot of caveating in trying to answer that question because we can't really pin down the explicit mechanism, but we have a pool of mechanisms that we think contribute. And so jumping back to this slide, so it could be GPS noise, it could be like errors that result from the conversion of the generation of the building polygon itself. But I will say the place where we see those errors the most intensely is as a result of what I would call the georectification process. So like the software system which takes the individual takes the individual photos and then builds the orthomosaic out of that. We see these misalignments come into play most intensely along the seams in those images. And so when we look at this photo, my intuition, I don't know for this specific photo, but my intuition is that the place where you see like these changes in the shape of the vector field, it represents a seam in the orthomosaic. But it's hard to say whether or not the seam is a result of GPS noise or like some errors inherent in the orthomosaic mapper, or if it's like, it's hard to provide attribution.
Mhm. Now, when you apply a correction, is it field by field? Is it building by building?
Yeah, so we go in and we annotate individual buildings, and then we use the adjustment that was generated for that building to also move the nearby buildings. And so this is a vector field in like the the truest sense, but it's more of like a Voronoi diagram in the sense that like these vectors are just the nearest neighbors to the one that we provided.
And last question, I'm assuming there are like translational errors and there are rotational errors too, right?
There's also scale.
I was just going to ask about that, if there's like scaling as well.
Yeah, there's scale, there's skew, and there's also shape. Like the building polygon could just be the wrong shape.
Yeah.
And in this case, we've only accounted for translational errors. And we think there's a path to synthetically train for rotation and for skew. Shape is a much harder piece though.
Yeah, you should talk to folks in the semiconductor industry because there are like, we could talk offline maybe if it's relevant, but there are like programs out there that I know at least for in that application area can correct for like rotation and scaling too. So, but when you brought this up, it was like, wow, I've seen something that looks just like this before. But
Interesting. Yeah, I'd love to hear about those details. We've seen instances where like medical segmentation masks follow a similar pattern to this, where like you've got an X-ray and you've got, I don't know, some other media, and you want to try and register the two. So like thinking about it as like a registration task. But yeah, if you've got literature or info, I'd love to hear about it.
cool, great talk. Thanks, Tom.
I have one more question on the more, you talked about, right, you started with the decision-making aspect and saying, okay, so I guess a few challenges that I saw throughout, right? You initially were talking about how the wireless connectivity, right, like often the bandwidth isn't enough to upload and download the data. And later on, you also talked about that was the bottleneck when you were analyzing, right, your current, the recent Helen and Debbie data sets. Do you think there is any interesting aspect here in terms of deciding what data to actually download or upload? Is there like maybe it's about resolution, maybe it's something else, right? Like that can be probed in a more adaptive manner to decide what data to focus on.
Yeah, well, I guess maybe to clarify your question, are you talking about like trying to prioritize the download of certain data given the constraints that we have, or like the transfer?
Yeah, that could be one, right?
Dr. Murphy may be able to correct me on this. I believe she's looked at that, or she's familiar with somebody who's looked at that. So I suspect there's value there, but I'm not sure of the specific literature.
So one is like, yeah, the type of data, like which one to prioritize, but the other is just like spatially, right? Like, I mean, you could zoom in on things that look like are the relevant ones and the ones that don't, and adaptively get more or less
Interesting. So like,
information for higher or lower resolution.
interesting. So like I don't know, let's say the model, or we have a model that says, okay, this area of the map is very important. We should prioritize the full resolution at this location. And then the rest of it's unimportant. We can send a lower resolution.
Yeah, and it may not be known a priori, right? Like which parts are important or not. Like as you start looking at the data, maybe you look at a lower resolution version and something seems like more or less. I know it's not an easy call, but yeah, are there adaptive
Yeah,
methods?
I'm not familiar with any, but I think there's some interesting meat there.
Okay, because that itself seems like a nice decision-making problem when you're talking about it, right? Like what data to actually.
So yeah, which data to prioritize? I mean, I think the hope here is that instead of transmitting the imagery, we can transmit the models of the label, and that's or excuse me, the labels of the model, and that's going to be a lot, just less like fewer bytes, so it'll be able to transmit faster. So if you can if you can do that type of analysis on the edge and send that to the decision maker, you can sort of shortcut this problem.
Right. And especially like if you couple that with confidence, maybe it's not as clear as just sending the label, but like something about, depending on how confident you are in the label, then you can send something.
Yeah.
Okay.
Yeah, I think that comes back to the calibration issue that you were talking about before. And there are a lot of other interesting problems that I think fall into or are blocked by having a really good calibrated model here.